Okay, well, hello everybody. I'm Tamara Galloway from the University of Exeter. And I wanted to start with a picture of where I come from and the terrible levels of plastic pollution that we have on our local shores. So this is Lantic Bay, which is just outside of our front door, and this is where we can go for a walk in the morning. There's always plastic there, so much plastic, as you can see from this image. But hang on a minute. If we go to other parts of the world, we can see that their perception of how much plastic litter there is in the environment is slightly different. The issue here being that plastic is everywhere, but there are vastly different levels of contamination affecting different parts of the globe. This picture, just to give you an idea that plastic absolutely is everywhere, was taken by one of our University of Exeter scientists 9 miles south of the North Pole. So this is on a piece of pristine sea ice. This is a piece of expanded polystyrene that's broken down, probably off an item of fishing or packaging gear. And there it is sitting on the pristine sea ice. So plastic is everywhere. But what we particularly want to talk about in this session, and what Martin has been talking about as well, are microplastics, things that break down from larger items. So we're talking predominantly about things that break down into fibres, into films, into fragments. On the left, you can see the fibres that have broken down from things like fishing ropes or from textiles, which we're also classifying as microplastics. And on the bottom right, microbeads that are deliberately put into products, which luckily we now do a lot less of. So all of these microplastics, one of the main issues that led us to be concerned about these things in the environment is that they overlap with the prey item size of many, many, many aquatic animals. So there are many animals in the sea which filter out tiny particles of organic matter. They can't discriminate, and they filter in these tiny pieces of plastic as well. And we can produce some compelling images. These are laboratory images, and these tiny animals, they might look insignificant, but these are planktonic species, so these are some of the most abundant animals on Earth. There are more of these than anything else, and they make up the base of the aquatic food chain. So what happens to them, how they're impacted, and what they ingest is extremely important for everything else that lives in the oceans. And at the top left, we've got a little copepod. Bottom left, that's a little larval oyster, in case you couldn't recognise it, this here. Little larval oyster, and it's got a little nanoplastic that it's ingested in its gut. We can see there. And on the right, what goes in must come out. We can see that plastics pass into animals, and they also pass out. And these are plastics embedded in the fecal pellets of planktonic species. And they act to take that plastic down into the ocean as a carbon source. We can move up the food chain, and we can start to see that whatever species we study and wherever we study it in the oceans, we can find plastics in their guts. We can find large pieces of plastic, and we can also find small pieces of plastic. The study at the top, we studied marine turtles, and we went to 3 separate sites around the world, the 3 main migratory areas. So we went to the Atlantic Ocean off Woods Hole, we went to the centre of the Mediterranean, and we went to the off the Australian coast of Queensland. We had students collecting washed up turtles and examining what was in their gut in post-mortem examinations. And lo and behold, we found that 100% of the turtles from all of those different locations had these plastics and microplastics in their gut. We can look at other species, other larger marine mammals, and we can see here this is a seal eating a fish. And we can study what's in the fish, and we can also study what's in the seal by looking at what comes out the other end of the seal. And we can find that in both cases, we find microplastics in the fish. And you can see that we've got fibres, fragments, and films of plastic that are present in the fish. And we can also see these being excreted by the seal. So what that's showing us is that plastics can pass through the food chain. They can be taken up at the bottom of the food chain, and they can pass through the food chain. So, of course, that gets us to the question that we've been asked to address in this particular topic. Well, are humans exposed to microplastics? How would we know, and how would we try to go about doing those studies? Certainly, some scientists have started to look at things that we eat from the sea. So they've started to categorise what kinds of microplastics you find in the things that you're eating. We've been doing some of this research in our own lab, but these are some results from Van Kouwenberg and Janssen. what they found is that they can take mussels. The top picture is mussels, and the bottom picture is oysters. And they can look at what they find in the flesh and in the guts of those animals. And you can measure the kinds of microplastics. This is measuring the kind of size range of the microplastics that you find in the gut. You can see mussels ingest slightly smaller particles than oysters. But if you do the sums and you look at how much you think that might relate to in terms of human exposure, you come up with figures such as 11,000 particles a year. So that's just one item of food, trying to estimate how many microplastics, if you ate those animals, you might be exposed to as a human being. But of course, in terms of human exposure, as we heard yesterday, you have to really know, if you want to be able to study what's happening to a human population, you've got to be able to understand what's in that population, and you've got to be able to understand the internal dose. And we might do that with something like the NHANES biomonitoring surveys in the US. Although they measure a range of different plastics-associated chemicals, they don't measure microplastics, because at the moment we don't have any methods to do that in humans. So you can go back to some of those studies in wildlife and you can say, well, let's do the next best thing. Let's look at what comes out of humans, because the idea there is what comes in must come out. And many of you may have seen these are some as yet unpublished results that have taken from an abstract that was presented last August at the Vienna Gastroenterology annual meeting. And this was a study from the University of Vienna. And they took a small survey of people. They had 3 men, they had 5 women. They're moderate age. They got them to fill in a food diary. They found that 6 out of 8 of them ingested seafood, so quite a high level of seafood ingestion. They all reckoned they'd come into contact with plastic packaging in the past week. And all of them had drunk from plastic bottles, with an average of about 750 mils being drunk. And when they looked at the results, they found that all of them were excreting plastics in their guts. It's a very small study, but it was telling you that in this very small preliminary study, there was evidence of plastic being ingested by humans. OK, so just because you're ingesting it, you've got a gut lining, haven't you? Isn't that protecting you from the effects of solid bits of plastic? Well, what happens in the gut is that you've got specialised areas within your gut that are there to encourage uptake of particles. So there are many parts of your food that you ingest which are nutritious but are in a particulate form. So your gut's got to have a way of taking them up. And you've got specialised cells in your gut called M cells. And here they are here. They've got narrow tops, and they're specialised for taking in different particles and passing them through into the blood and to the lymph nodes. Here's a picture of one there, an M-fold cell. And we know from studies of microspheres which have been used to take drugs and use them as drug delivery systems that you can target these M cells and you can encourage uptake through these M cells of microplastic-sized objects. So we do know that they're taken up. And a couple of studies have started to appear of what might happen in vertebrate models. We don't have any studies of humans yet, but this is a study from a group who've been studying chickens as a study model of what happens in the vertebrate gut. And you can see here is the M cell region of the gut in these chickens, and you can just see that there are tiny little microplastics embedded there. These chickens have been exposed to microplastics along with food, and if you just look here, you can see that they've been exposed to 2 mg per kilogram of microplastics, and you can just see a little number there. That's 10 to the 9 polystyrene spheres per centimetre of intestine. So that's comparing with the 11,000 particles a year that we think that humans are being exposed to. And what they found in this particular model was that when the chickens had been ingesting large numbers of microplastics, they remodelled their villi. So the lining of the intestine changed slightly, and the villi became more leaky. And when they looked at the uptake of different nutrients, they found that the uptake of nutrients, and particularly iron, had changed. So by ingesting these microplastics, it had altered the physical structure of the villi in the gut. One other study, and this is looking at, again, yesterday we heard about microbiomes and we heard about how important they are to our health. This is a study that was done in laboratory rodents, and this study was done in China. What the authors did here was they exposed their mice to nanopolystyrene particles. Here again, you can see 100 micrograms per litre, so 200-fold less concentrated than the previous study. But again, they looked at what was happening to the physical structure of the gut. They found that the physical structure was changed, that the mucus layer that was protecting the gut from all of the things that were passing through it was altered. So the mucus cells were secreting less mucus. And they also looked at the makeup of the bacteria, the families of bacteria that were living in that mucus that were protecting the inside of the gut. And they found that the microbiome had changed. It had altered. And the alteration was enough to cause sort of physical changes in what that microbiome was likely doing in terms of health. So you can say that both the barrier and the microbiome can be changed if you're exposed chronically to plastic particles in your diet. But a quick look at the size of those particles, micro versus nano. Not all of the particles that are present in the ocean we'll be able to see, because some of them break down into smaller and smaller particles. So here are some particles. This is a typical microbead from a shower gel. You can see when it's synthesized, it's quite smooth and round. Here it is after it's been in the environment, been weathering in seawater for a while. You can see it's starting to break up and it's got a more jagged physical surface. And here are some results from Albert Coleman's laboratory, where he's taken the surface of polystyrene and looked at it after several weeks of weathering. And you can see that there are little tiny particles breaking off the surface. And these are little nanoplastic particles that are breaking off the surface of the polystyrene. And to cut a long story short, if you do lots of modelling studies and you do sort of laboratory studies, we've estimated that about 80% of the plastic that we've thrown into the sea, that we can see in all of these different areas washed up on the shoreline, 80% of it is too small for us to see. So 80% of it is in nanoform. Why is this important? Well, it's important because nanoplastics can be taken up across the gut much more easily than microplastics can. They can be taken up across the gut and they can be taken up into cells. And these are some results from our own laboratory. These are embryo zebrafish, and the zebrafish have been fed fish food that's got little concentrations, small concentrations of nanoacrylic polyesters in them. And these acrylic nanoparticles are used in packaging materials and they're used in building materials, and we were testing their effects if we put them into fish food. And we can find that not only can we find them in the inside of the intestine. These are some results that used a special imaging technique. So if you go to the doctors and you get yourself imaged, we were using similar techniques to be able to see where those plastics went without having to cut the animal up. And we can see that they're present in the intestine and they also pass into the liver. And we can also see that they can pass from the liver. We can see them actually inside of cells. So this is the inside of a cell. These are some of the subcellular organelles, and here are some of the plastics. Okay, so my time is up. Does it matter? I'll have to speak really, really quickly. Does it matter? We saw earlier that your average human being might ingest 11,000 plastic particles if they were an avid seafood eater and they like to eat seafood. What does 11,000 plastic particles look like? Well, it's about a quarter of a teaspoon. It's a tiny little amount of plastic, so about 7 micrograms. If that plastic had absorbed PCBs from the ocean, how much PCB might it add to your diet? It might add about 0.2%, as Martin's already said earlier, to your total load of PCBs from everything that you eat. It's important to note that there are many other contaminants in seafood as well. It's not just microplastics, but there are many other things. So these graphs show you the average the average contamination of seafood with other organic chemicals, DDTs, pesticides, PCBs, and other things. We simply don't know what the ratio between those contaminants in seafood is and the presence of microplastics. Think again, we've talked about nanoplastics uptake in the food, but it's been estimated the average person's exposed to about 1 trillion man-made nanoparticles every day in the food that they eat. And these are just some pictures. These are some macrophages with aluminosilicate aggregates in them taken from human intestinal lymphoid cells. And on the right, these are some of the things that contain some of those nanoparticles like titanium dioxide and your average dose if you had an average portion of them. Finally, final slide, exposure from packaging is very hard to avoid. So these, again, are some results from our own laboratory. We tried to do an intervention trial. We enrolled 120 local school children and we got them to design their own intervention trial that included no packaging and followed all the government guidelines for how to reduce your exposure to plastics additives and did everything that the government told them to do. And at the end of the 7-day exposure period, we saw no difference in the levels of plastics contaminants in their blood at the end of that trial. And what they fed back to us was it was impossible to do. They couldn't work out how to eat things that weren't wrapped in packaging or how to go out and eat in the canteen and know that what they were eating hadn't been exposed to plastics. It was almost impossible for them to do, suggesting that better labelling is something that we really desperately need to do. So sorry I've gone over time, but thanks to everybody in my lab, and I'll move over to the next speaker.